Good morning, everyone. Thank you for coming, and welcome to the second of our two series of final presentation talks by this summer's students. This year, we've had students mostly from California, but a few from all over the country who have come and joined us and spent 10 weeks doing a scientific research internship, paired up with a member of our scientific staff here. This morning, you'll hear from 6 students. Each student will give a talk that's about 15 minutes long, and I encourage questions afterwards because answering questions is a big part of the experience in giving talks. So ask some good questions, please. So our first talk today is by Rachel Hatch, who's from Cal Poly Pomona.
All right, good morning, everyone. My name is Rachel Hatch, and my mentor is Dr. Cristina Dalle, and I will be presenting today on my summer project, which was analyzing surface conditions on Enceladus via infrared spectroscopy, the process of creating mosaics, and more. All right, so a brief intro to Enceladus. It's a very unique ice world. Although it's relatively small, only 500 kilometers in diameter, it has a very high albedo, reflecting almost 80% of the sun's light. And it also has active geology and regions with varying terrain. So as you can see, in this north corner here, you have a lot of crater terrain. So this is generally thought to be older. Also over here, we have some fractures with some intermediate age terrain. But the most interesting terrain on Enceladus is the south polar region, in which there are the tiger stripes. Now, at these tiger stripes, there are actually plumes of active gas and ice being expelled from these fractures. Scientists believe that there is a regional ocean beneath these plumes, thus the active geology. And the regional ocean is being kept up. Scientists have studied this by either both a 2-to-1 orbital resonance with Dione, which is another one of the moons around Saturn, and also its eccentric orbit around Saturn, and that produces tidal heating to keep a regional ocean. So basically, scientists are looking at Enceladus as a possible source for life. So here's some more on Enceladus. The gas plume contains mostly water vapor and has some carbon dioxide, some methane, some ammonia, and also small quantities of heavier hydrocarbons. As you can see, these beautiful Cassini pictures of the south polar region. You can see the plumes over here, and with the sunlight in the back. Thanks, Cassini, for those awesome images. But the presence of ammonia in the plumes was actually a pretty incredible find, because ammonia can act as an antifreeze, which again suggests that there is a regional ocean beneath the south polar region. So here's another pretty picture of Enceladus immersed in the E-ring. I chose Enceladus because of its active geology. Before this summer, I honestly could say that I had no idea Enceladus existed. So it was a great find, and we decided to do a spectral analysis of Enceladus' surface. So I did this by selecting Cassini VIMS data from a website and creating mosaics, which basically means taking that data and putting it together to make a bigger picture, basically puzzle pieces, putting it together. And then I clustered the data to actually analyze what was going on spectroscopically, or using spectral analysis. Okay, so my data set was the VIMS data set from the Cassini mission. The VIMS stands for Visual and Infrared Mapping Spectrometer. So the VIMS instrument takes a visual image and also an infrared image and produces a cube. And I'll go into cubes in a moment here. I selected the data from Planetary Image Atlas website, and basically I had put in parameters of latitude, longitude, and also pixel resolution. I wanted to focus more on the tiger stripe area, so I tried to find cubes that had good information in that area, and that proved to be sort of difficult. But the most important parameter was probably the pixel resolution. We wanted to make sure that when we clustered the data and derived information from it, that we could get good resolution on the composition. So then cubes. So here are some examples in the lower left-hand corner of cubes I used for a mosaic. So you can see these are pixelated images, but what is a cube? Cube is basically an image. So lines and samples is the two-dimensional image, and then bands is the three-dimensional depth part. Bands are basically like wavelengths, so you can view the image at different wavelengths, and thus you get spectroscopy. So mosaicing, I first used Envy to mosaic, but that proved to be very difficult, and it was too time-consuming, so I decided to learn how to use ISIS, which proved a lot more fun. It was Linux-based, but once I got used to Linux, I really enjoyed ISIS 3. So what is the process of mosaicing? Basically, I would select which cubes I wanted to use. I then divide the cubes into a visual and an infrared image. And I didn't need the visual images, so I just used infrared information, which was the spectroscopy information. I then attached the information to the cubes. So each cube had certain geographical data that I needed to make sure that was on the cube, so the cube knew where to line up on the map projection. I then created a map file using various projections, and I then project the images onto the map file, and then I put all the puzzle pieces together, and you get your mosaic. And here are some examples of the mosaics I generated. These are all of Enceladus. In this cube is a 1604 flyby. This one's the 1500 flyby. This one is the 1637 flyby, and to the lower right is the 1660 flyby. Originally, we were going to try and compare different flybys to see if time-wise, if anything changed in the data, but as you can see, the resolution in the tiger stripe area isn't the same in each flyby. So we decided to just do the analysis on one, and the 1500 mosaic is the one we eventually chose to cluster and derive some information from. So this is the final mosaic that we got. This is in a Lambert azimuthal equal area projection, which is why it's different than this equal equirectangular projection, but it's the same cubes. You can clearly see the tiger stripes at the bottom of the image, running about a little east and south, about 30 degrees. And you can even see the intermediate area, intermediately aged area with these fracture, and then the cratered region over here. So now that we have this final mosaic, what do we do with this? How do we get the information? So next was clustering. So what is clustering? Each pixel that you see in this mosaic represents a line in this graph. So you can see the spectral lines going across all the way to about 3.5 microns. So clustering basically takes those spectral lines and groups them together in subgroups in which they have similar spectral patterns. I'll get to a better example of that on the next slide. But to cluster, I used IDL codes, which was really fun. I didn't have any issues ever with IDL. So that was a great learning process. And here's a good example of what clustering actually does. So clustering took those spectral patterns and subgrouped them into other classes. And they put them into an average so you can get a better idea of what's going on the entire surface of Enceladus. Another process that we had to deal with in clustering was normalization. The image on the left is an unnormalized cluster. Normalization accounts for the illumination of Enceladus, or whichever satellite you're working on, and basically make sure that it's all starting from the same plane. We also had to filter out the noise. So this was this is normalized, but as you can see, these pixels over here weren't very good because they didn't fit with the other information. So basically we had to filter out that noise and then rerun the process and then get our good data. So this is our results and conclusions. As you can see in this very pretty picture on the upper left-hand corner, there's 4 distinct colors. So you have this teal at the tiger stripes, and then this maroon just around the South Polar region, and then the blue in the intermediate area, and then the pink in the older terrain. And here's just a reference of the original mosaic. So what does this all mean? Why are there spectral differences on Enceladus? And our conclusion was that the grain size was different. And we concluded this because of this spectral analysis graph right here. So this spectral graph corresponds to the clustered mosaic. And the teal here is at the highest, and then it goes maroon to blue to pink. So the teal is has the deepest band, and this is actually the 2-micron band right here. Unfortunately, I did not have time to edit the axis, but the 2-micron band is a water band, and the deeper the water band, the larger the grain size. So as we can see, the teal is the deepest, and it has the largest grain size, and then the grain size goes finer and finer as you go further out. So some of the future work that we might do is look at more recent flybys. I know there's a Cassini mission that's going to happen in 2015, so hopefully we can get some good VIMS data and be able to compare it to see if there's a time span difference. Also hypothesize as to why the grain size differs on Enceladus. Another future project is also to determine the amounts of amorphous and crystalline ice. We can look for phase changes and look for heat changes on the satellite, and then apply this method to other satellites around Saturn using Cassini data. And I'd like to thank my mentor, Dr. Rudolph, also Dr. Cynthia Phillips, for running this amazing program, also my parents, and then the Camp Prayer program in general. So thanks, guys.
Great, nice job. Okay, do we have some questions for Rachel?
Oh.
Yeah, so you found that there are varying grain sizes on Enceladus. So what are the implications of such findings? Does that affect the possibility for extraterrestrial life in any way?
Well, for the most part, we're just looking at the basics. The changes in grain size meaning is more closer to there's a changing in energy and heat around the tiger stripe areas, and it varies. And where there's heat, there's water life. We're kind of in the step 1 of a 15-step process for looking for life. So.
Okay, others?
So what did you really do this summer?
So what I really did this summer, I met awesome people, went to awesome places, used awesome instruments, and looked at awesome rocks. So it was just awesome. Yes.
The looking at rocks, does that relate to what you just presented here, or is that a different project?
No, that's
Okay.
that's just cool.
Rachel, you used the term mosaics. What you showed, though, unless I'm wrong, was the reprojection of a single one of the images, or did that include the composite of several different VIMS data sets?
This, in the lower left-hand corner, that was some of the cubes that I had. I then took some of those cubes and images and put them all together to create these mosaics.
Okay, fine. So it truly is a mosaic in the sense that it's composed of different
Yeah.
components. Thank you.
Yeah, no problem.
Other questions? Okay, let's thank Rachel again. Nice job. So our next talk this morning is by Gabriel Garcia, who's from the University of Texas Pan American, and he'll be talking about his Mars-related project.
Okay, so hello everybody. My name is Gabriel Garcia, and this summer I was working with Dr. Lori Fenton in determining the dune-constructing wind regime in eastern Olympia Undae on the North Polar region of Mars. So let's get into that. So just to give you a little bit of an outline, the nature of the winds in the North Polar region is starting to change the previous morphology of the region. So we're trying to figure out why. What's going on here? What's different about the region that's starting to cause new winds to take over, more or less. So in order for me to do this, I'm going to describe some background information about dune formation. We're going to question some of that background to try to figure out what is different, what's happening, what we can determine from this. And we're going to then go into the study area that I observed throughout the summer and go into the method of how we're going to analyze the data that we processed from this, then go into the results we got and the conclusion and how we can do even more in future steps. So just to go into very beginning dune formation processes, dunes form through a process known as saltation, which is just the bouncing of grains off of the surface as the wind blows it along. When you get enough sediment accumulating, you'll get a dune that forms. So if you look at this graph, these are different types of dunes that form, but the only two that I really want to go into are these two right here. So if you look at this one, where is it? Here we go. This is known as a transverse dune. So you see how you have wind going in one direction? This type of dune forms in a unidirectional wind environment. So the wind is orthogonal to your crest lines, which are right here. So as you get more winds involved, you can get longitudinal dunes right here, which is when your winds are at an angle greater than 90 degrees. They're coming together, and they're forming parallel dunes in a very straight line. And of course, these are very extreme, perfect examples. And of course, in nature, we don't get perfect examples. So in most cases, you'll get something known as an oblique dune, which is just somewhere in between. It's not necessarily transverse. It's not necessarily oblique. It's just right in the middle. So again, for longitudinal, both winds have the same strength. So they're, I guess, pretty much pushing against each other. So oblique dunes don't necessarily have to be that way. One could be stronger than the other, and you'll get something in between longitudinal and transverse. So that's a general case. Okay, so as I was stating earlier, this is a graph that's representing different dune forms that type given a transport ratio, which is the strength of one wind compared to the other, and a divergence angle between those two winds. So anything below 90 degrees will give you a transverse dune. It's only when you go above 90 degrees that you get very interesting differences occurring. So like I said earlier, at a 1-to-1 ratio, you're going to get longitudinal dunes that form because they're the same strength and they're pushing against each other, forming these parallel dunes. At a 16-to-1 ratio, meaning one wind is 16 times stronger than the other one, you're going to get transverse because it's kind of like the other one's not even present. And in between those, you have oblique dunes occurring. So it's just an in-between formation. If you look here, reversing dunes are technically transverse. It's when your winds are either colliding together or going exactly opposite. So they're going to get transverse-like properties, but they get their own category, since it's technically not one wind environment. So this summer, I spent 8 weeks mapping out dune crest lines using a geospatial information system software known as JMARS, using high-resolution image science experiment satellite data. So my setup here is I have 2 computers going. My hardware was not necessarily fast enough to process the data. So while one had the picture loaded, and while I was mapping out these dune crest lines, the other one was either loading in the background. So I was just switching back and forth to get as much data as possible within the time that I was here. OK, so this is the study area for the work that I conducted. This is the Olympia Undae dune field in the North Polar region of Mars. And as you can see here, this planum boreum is your polar ice cap. So just to note, north is down for this picture. And previous work has been conducted here, more or less in the middle of the dune field. And my work was spent within this region, but more towards the very eastern edge of the dune field itself. So the purpose for this location is because if you look right here, it's kind of hard to see, but there is an erosional feature right here. And this could possibly be bringing winds that are affecting this dune field. So it's a more northerly wind. So the reason we chose this spot was because it's behind that feature, so we can compare if we're getting dunes similar to that, that there's something beyond that wind that's affecting the area altogether. So this is the actual image that I spent mapping. Of course, the left is unmapped, the right one is mapped, and each dune set was divided based on the type. So for our primary dunes, which are the very north to south oriented orange dunes, we believe they're transverse. All of the types here are inferred. We don't really know for sure because it's just imagery, but from our best knowledge, we believe that these are transverse dunes. And then our secondary dunes, which are younger features, which seem to be overtaking the primary dunes, are believed to be longitudinal. More work is still needed to be done there to really confirm that. But for now, we believe they're longitudinal. And then our coarse grain ripples are even smaller features, which are within the bottoms of the dune field themselves. So this was what we believe to be underneath the actual dune sediments. And then the smallest features are the sand ripples, what change readily and most easily as winds change. So to indicate recent winds, this is what we're going to be looking at most. So this highlighted area is where we'll be looking at. It's just a zoomed in picture to give us an example of all 4 of these types in one area. So this is the area that I just mentioned, except it's unmapped. So if we look at what I did, here we have all our different dune crest lines. So our blue ones are the ripples, the fine ripples. The red are the coarse ripples. Orange is primary, and green is secondary. So from this, there is a dominant easterly wind coming from this direction. So we inferred this due to noting little features in the morphology. So there's things known as slip bases, which when enough sediment accumulates on the dune peak, gravity takes over and will pull the sediment down. So because we're only observing these slip bases on the western side of the dune, we believe that there is a predominant easterly wind influencing the dunes. And we can also infer this by our sand ripples. So the blue ones, you can see they're all north to south oriented, and this is leading us to believe that that's the dominant and main wind that's influencing our area. And of course, as you involve more sediment, it requires more time to really change or affect that dune in general. So the next one that would be affected would be our coarse ripples, and then the secondaries, and then finally the primaries, which could take up to thousands of years. So they're very large features. So after we map out all of our crest lines, we get things known as rose diagrams, which this just averages out all the crest lines for each set that we mapped, and then orients it in this pattern. So if you look at this diagram, north is up, east, south, and west. And this is the average of all of our crest lines for our coarse grain ripples. And of course, we're going to have deviations from the actual average himself. So each of these little spikes represents that deviation. So that could just be minor curves in the actual crest line itself towards the edges. But for the most part, this is our average trend. And if you look at previous work which has been done, our average is a little bit different. So as stated earlier, this could be caused by a northeasterly wind from this erosional feature. So as you can see, you have darker sediment coming down, and of course, warmer rises, cold air falls. So then this air is going to be channeled through this dark sediment and give these areas over here a more northerly wind component, which is going to overall reshape these. So as you can see, the sand ripples have a completely different orientation than what we found here. So this could be the main reason for that. But if you look at the primaries and secondary dunes, those are more or less the same. You can see how that northern wind would have an influence, but it's not that different. It's close. And then if you look at our secondaries, those are still pretty close as well. So if our area is not being influenced by that northerly wind, what's creating these secondary dunes? It's got to be something else. That northern wind could help to influence those or maybe change the angle of them a little bit, but it appears as that isn't the primary source for what's going on here. So in order for us to determine that, we have to go into more of the orientation for our crest lines. So manipulating a rule known as maximum gross bedform normal transport, what this does is, given wind data, it's going to give you your bedform trend. So what we're going to do is, since we're using only imagery, we don't have that wind data. So we're going to invert it to, we're going to put in information about the bedform trend, and then it's going to give us information about the wind directions and the possible wind strength as well. So if you look at this example over here, you have our bedform trend aligned this way, and you have one wind, Q1, and another wind, Q2. So if you just add those two vectors together, you'll get a resultant drift direction, which is this way. And if you superimpose these two winds onto this value t, that is maximum gross bedform normal transport. So this value is maximum orthogonal to your bedform trend itself. So you can see that this would be more or less an oblique dune environment. If the resultant drift direction was parallel with your bedform trend, that would mean that your Q1 and Q2 are equal strengths, and that would be a longitudinal environment because they're not, the angle between them is greater than 90 degrees. So this is an example of an oblique wind regime. So we're going to use this process to try to determine the nature of our primary dunes. So this is what we ended up with. This black line represents our primary dune crest lines, and this is what we know. From observations of the imagery, we know this bedform trend. From analyzing our rose diagrams for the wind ripples, we have inferred that there is a wind coming from the east-southeast direction at 95 degrees that is helping to form our primary dunes. And the next step would be to try to guess as to what's other possible wind is helping to form our bedform trend. So each of these colored little blotches represents one other possible wind that can form or help to form our bedform trend. So from analyzing the morphology, we believe that there is no southerly influenced wind in forming our bedform trends. So that's why these are all faded out. That's not a possibility for us. So if you look here, each of these numbers represents a transport ratio. So remember, 1-to-1 means both winds are just as strong. So we believe that since there is not a huge deviation in the wind ripple orientations, that our wind ripple wind speed has to be much greater than our second unknown wind. So that's why everything 1-to-1 and above is also faded out, because that's not what we're observing. So we've narrowed it down to this bold area here from 1-to-2 to 1-to-16, which means our known wind is either between double the strength of our unknown wind or 16 times stronger than our unknown wind. And this is going to combine with our inferred wind to create a transverse wind environment that's going to create our primary dune trends. So this is just the first step in analyzing the real nature of the wind environment. And hopefully later on, we can determine the nature of the secondary dunes. And if it matches up with our primary dunes, then that's a really good chance that there is a new wind coming from this erosional feature all along this entire cliff, which will add to our easterly wind to create our dune environment. So that's future work to be done, but it's really interesting to see how these differences change from maybe a 500-kilometer range. This is a huge area, but it's just interesting to note that. So these are the references that I have. I'd like to thank NASA and my program for accepting me into this program and the funding. I'd like to thank SETI for taking me into their institute and teaching me and just providing me with a good work environment. I'd like to thank my mentor, Dr. Lori Fenton, for putting up with me for 10 weeks and making me wonder about the really tough questions. And I'd like to thank James Brewster, which is the IT guy here, for helping me with all of my computer issues for the very beginning part of the program. So thank you for listening. Any questions?
I'll start with a question, actually. So there was there was the existing feature that kind of had a northerly wind toward the first study area.
Right.
So was there a topographic feature or something that blocked that northerly wind from getting to where your study area was? I wasn't clear as to why the area you were looking at couldn't be influenced by that wind.
Okay, so as earlier, we chose this spot entirely because it was behind this feature. So of course, all the white is the polar ice cap. The erosional feature is up here, and all this is the sediment that has eroded and deposited down through the polar ice cap area to affect this region over here. So we're not seeing it here, otherwise we probably have darker sediment all along here as well, indicating that it's just sweeping out from that erosional feature rather than just being funneled down in one direction.
Okay, so is that a cliff or something, that
Right,
bright
this
part
is
there?
also
Oh,
an
okay.
erosional feature,
Okay.
but this would probably not be affecting this area as much as ours.
Okay. Cool. Other questions?
Yeah, on your earlier slide, can you go back to that one where you showed the transverse, the longitudinal, and the oblique dunes?
This one.
And the other one?
This one?
Yeah.
Okay.
So that examples seem to vary immensely. I was wondering, can you give us like a colloquial definition of a dune? Let's say if you was going to explain to someone who wasn't as scientifically savvy.
Right, so all these are different types of dunes in different wind environments. So if you look at A, C, and E, these are all in dune environments that form in a unidirectional wind environment. So one wind from one direction all the time. So only difference between these is the amount of sediment available. So if you look at A, these are known as barcans. So in environments that have very little sediment, this is what you would see first. As more sediment accumulates, it kind of transforms into a barcanoid, which is E. And then as you get even more sediment, it turns into C, a transverse dune. And there is also one more environment which deals with one wind environment. These over here are called parabolic dunes. But these only form in the presence of vegetation. So the sand's going to grab onto the plants and sweep out the remaining material to form this parabolic feature.
Yeah, you're telling me how dunes is formed. I want to more so know what is a dune.
Right, so a dune is just an accumulation of sediment through a process known as saltation. And saltation is just when the wind blows, these sand grains bounce along the surface and accumulate. Depending on the grain size, they can either be suspended in the environment if it's a very fine-grained dust, or there's things known as creepers, which is just larger sediments, which just bounce or just kind of roll along from being bombarded with smaller grains.
So it's basically a pile of sand that's blown and shaped by the wind?
Yep.
So did you find any evidence for sandworms in your data?
I did not, unfortunately.
Okay, great. So clearly you're interested in the winds. I mean,
Right.
you're using the dunes to learn about the winds.
Right.
And so it seems like you're saying when you went back to the slide, one predominant wind all the time, and so
Right,
the
that-
issue, it's not so much an issue where you might have winds converging all at once, because that's a little hard to do. But maybe it blows this way one day and blows another way another day, and it's
Right,
kind
the
of
wind, if
variable.
you've been outside, which I'm hoping you guys have been outside, the wind never blows from one direction all the time. It may shift and blow in other directions, but it varies. It changes and it varies, so it's never from one direction all the time.
But you're interested in prevailing wind patterns. So, I mean, for example,
Right, so this
where
could
some
mean-
of us live in LA, the wind is usually from the west,
Right.
if it's blowing.
So this could mean during the day it's in one direction, but maybe during the night when it gets cooler, the winds may change and then go in a different direction.
So I was still trying to understand why we think that erosional escarpment feature is the source of the wind. Is it because it's a darker albedo, so you think the
Exactly.
air above it is hotter, and then
It would
the
be a little bit
surrounding
warmer,
area?
so then those winds are going to be funneled down that darker sediment for that specific reason.
Is part of it also that the process of erosion actually releases gases that form the wind? I mean, does that increase the atmospheric pressure locally, or are you just talking about you're tracking the direction from the dark sediment that's released?
I'm really unsure about that process, but I'm sure that that could play a part in how the winds start to flow in different directions as well.
Other questions? Okay, let's thank our speaker. Nice job. So our next talk is by Jill Walker from Cal Poly Pomona.
Okay. There we go. Good morning. My name is Jillian Walker. I'm from Cal Poly Pomona, and my mentor was Richard Quinn with SETI Institute and NASA Ames, and today I'll be telling you about my summer project, which was OREOcube. OREOcube stands for Organics Exposure in Orbit. It's an astrobiology experiment that's taking place on the International Space Station. It is an international collaboration between NASA and the European Space Agency. Earlier in the summer, I had the pleasure of working with some of our colleagues, Dr. Pascal Ehrenfreund and her postdoc Andreas from Europe, so that was really interesting. And we're studying the interaction between minerals and organics, and we're particularly interested in how these compounds interact in space radiation environments. And to do this, we'll be deploying a payload on an external platform on the International Space Station. And so while the space station is in low Earth orbit, we are interested in extrapolating the results of our research into different space environments, such as the interstellar medium, star-forming regions, the Earth-Moon system, and especially Mars and other outer planets and moons. And so this is our payload. It's a 10-centimeter cube, and we're putting two of them up on the platform. And each cube has 24 sample and reference cells on this little carousel here. And each cell contains an organic and an inorganic film. There's an inorganic and then an organic film placed on top of it. And they are hermetically sealed microenvironments. So each cell is like a contained little environment in itself. It's airtight. And the way we measure changes in these samples is by UV, vis, and near-infrared spectroscopy. Now, the interesting thing about experiments on the space station is that usually exposure experiments are done by leaving a payload out on an external platform for a year or so. And then the payload is retrieved and then data is collected. However, OREOcube will measure spectroscopy in real time. And we do that by, let's see if I can get this mouse working. The spectrometer is down here in this bottom third of the OREOcube. And then the samples are on a carousel that rotates up here. So as the carousel rotates, we can get different measurements of different samples. And so this is a cell in itself. So we have two windows that seal the edges. One is a aluminum oxide window or a sapphire window. And that is down at the bottom here. And that we chose for its physical strength. It's very strong, it's very sturdy. We have a metal spacer that actually creates the chamber in itself. And then we have the magnesium fluoride window, it's a more fragile window, but it allows for a wider range of wavelengths of light to come in. And so we first deposit an inorganic film, a thin film, on the inner surface of the mag fluoride, and then we deposit inorganic on top of that. And that is how our inner reaction cell environment is created. So for the microenvironments that we're working with, we have, there we go. So we're working with an inert gas called argon, and that is the gas that is in our reference cells. And this is meant to simulate the interstellar or interplanetary medium. We're also working with different, the inorganic samples that we're working with are hematite, magnetite, iron, nickel, titanium oxide, and chromium. So, and we are using these minerals to create analogs to reactions that can take place in other planets or moons, asteroids, or protoplanetary disks. And while we're not working with gases or humidity in these experiments, the OREOcube system, the setup for the experiment, is actually very robust and very flexible. We can use it to study any number of things like changing the gases in there or altering the humidity and seeing how that changes the reaction rates of the compounds inside. So we have 3 organic compounds that we're working with. This one right here, isoviolanthrene, is a polycyclic aromatic hydrocarbon. It's similar to what is found in the interstellar medium and regions of star formation. And we want to study this because it'll give us a good idea of what kind of reactions are going on in the interstellar medium and the mechanisms of these reactions. Anthrorufin is also a polycyclic aromatic hydrocarbon, but it's much more oxidized, so it's going to be a little bit less reactive. And then my personal favorite is we have iron tetraphenylporphyrin, or just iron porphyrin, and this is sort of an analog to hemoglobin. It's very biologically relevant, and by understanding the changes in hemoglobin that are undergone by photocatalytic reactions, then we can understand a lot more about how these things might be formed or how they might be changed in space. So this is, these are a couple photos of the flight cell construction. The entire process was done in argon. Our cells were never exposed to the laboratory air. So we used a vacuum chamber, which is right here. This is a vacuum organic deposition chamber. And we take it down to really low pressure and then sublimate our thin films on it. And it's just like evaporating water onto a surface. And so this is what the bell jar looks like when it's opened up. And our samples are on there. We can do about 30, 40, 50 at a time. And in that way, we can start to create our cells. And each of these cells is handmade. The interesting thing about this is that each cell takes about an hour to make, and we have 6 people working at any given moment. So technically, it takes 6 man-hours to create one cell, and that's just for assembly. That's not including deposition. That's not including leak testing, which takes another hour afterward. And it's not including the characterization of the thin films themselves. So it's a very time-intensive process, and I was really excited. We started leak testing, and I was actually terrified because we had a 50% failure rate on the testing for the leaks to see how airtight they are, to see how contained the cell actually is. And at the beginning of it, we were at like 50% failure rate, and now we're down to less than 10, so I'm thrilled about that. And so these are a couple more photos of the assembly process. This is about halfway through. We use these blocks and these loading dies to set things in and to get them all aligned. And these are what the samples look like when they're done. They're beautiful. And so I say that these are organic thin films and inorganic thin films, but it doesn't look like there's anything there. That's because they're optically transparent. They're so thin that you usually cannot see them with the naked eye, but they do show up on spectroscopy. And so that is what we're doing. So here's a closer up. This is a close-up of a completed cell. Here's the magnesium fluoride window here. And you can kind of see it here, but there's an indium. Indium is a soft, malleable, very flexible metal that we're using to seal the entire cells together. And so there's an indium seal, the spacer, another indium seal, and then a sapphire window at the bottom. And so when these samples are out on the space station, what will happen will be that sunlight comes in from the space environment, comes through this mag fluoride window, and when it hits direct straight on, it will come down into this chamber and be picked up by this optical fiber, and then spectroscopy will be recorded. And so the kind of results that we're expecting, I just want to explain one thing before I go into this. Titanium is the metal that we start out with, but we turn it into titanium dioxide by annealing it. Titanium is very reflective. This is the absorbance, so it's very shiny. But by heating it and by oxidizing it in a furnace, we change the absorbance spectra very much. So titanium dioxide, which is the film that we actually work with, will look something more like this down here at the bottom. And the kind of data that we're expecting to see is going to look more like this green line right here, which is more like the iron porphyrin graph. But to see these changes is what we're looking for, and to be able to record these changes and see how it alters over time is going to be very important, and we can see what kind of reactions are going on. So I'd like to acknowledge we have a huge lab, so many people, Katie, Andy, Pascal, Erwin, Freund, and Andreas, and then all the undergrads I worked with, Alex, Joanna, Griffin, Devin, Keegan, all wonderful people. Then NASA, NSF, and Kemper, and my professors back home. Thank you. Any questions?
So can you tell us when this is going to fly?
We're hoping either late 2014 or midway 2015. Is that about right?
We're waiting for ESA to catch up to us. They're being built by industry. The flight unit is being built by industry, so we're hoping within the next year.
Cool. Other questions?
Jill, I thought I heard you say that the argon environment was supposed to mimic the interstellar medium. Did I misunderstand that?
I think that might have been what I said. Yeah.
Okay. Certainly, if I were thinking about the interstellar medium, argon wouldn't have been the atom that I would put, or the gas that I would put there. And also the interstellar medium is slightly ionized, which could have some impact on the chemistry.
Okay.
Can you explain the choice?
We chose argon mostly because it was an inert gas, and we wanted to remove any chance that we were seeing oxidation because of oxygen in the atmosphere in the cell that was put there by laboratory air. We wanted to make sure that we were seeing catalysis between the metallic thin film that we put down and the organic that we put down, not something else. So it was sort of a control.
Other questions?
All right, so you said that your device was going to be doing spectroscopy in real time.
Yes.
So what are you hoping to figure out or learn by doing this spectroscopy in real time?
We're hoping to get a more exact picture of what's going on. I'm sure that we can line up any interesting changes in the spectroscopy to maybe changes on the space station, or maybe the declination or something, and to see how, if there's any correlation between them, or simply to see the reaction rates. So yeah.
So you're basically going to watch how these various substances change and sort of degrade over time as they're
Yes.
exposed for longer and longer?
Yes.
Okay. Cool. Other questions? Okay, let's thank Jill. Nice job.
Thank you.
Okay, so our next talk is by Frank Garcia, who is also from Cal Poly Pomona.
Good afternoon. My name is Frank. I'm going to talk to you about the radio astronomy and how I observed Blazars in the Galactic Center. And I worked with Gerry Harp this summer. So what did I do? So this summer, I was observing Blazars and the Galactic Center using the Allen Telescope Array. And with this, the data process, I imaged radio images with the data. So the Allen Telescope Array. The Allen Telescope Array is right now currently has 42 6-meter dishes around Hat Creek, and the farther away the dishes are, the more a field of view we can get. So when I say we observe radio waves, I mean like in the electromagnetic spectrum, we're observing around the 6 to 9 gigahertz because that's over the RFI, the radio frequency interference. It's actually a lot closer to the microwave, and it's around here between the radio and the microwave place. And each telescope has its own field of view, and we put them together. It's larger, and at the focal point of each parabolic telescope, it's actually the center. So when we put the telescopes together, we could get one focal point for the amount of telescopes we use. So, and the delay of the telescopes is also has contributed to how much we can see. As you can see, that's a representation of the Allen Telescope Array and how it works, although it's not exactly lined up as such. And this is the antenna we use in each telescope. This is the older antenna. We're hoping to replace it with a newer one, such as that one. And if you can see at the top, the frequencies or the wavelength is smaller than we could see from the bottom. And again, we observe around the 6 to 9 gigahertz frequency. So what do I observe? Well, this summer, I started observing quasars and blazars. And a quasar is basically a really large light coming out of a black hole. It's an active galactic nuclei, the black hole, that's still undergoing its process of making this something. And it's, as you can see, it's radiating a lot of magnetic fields and light thanks to the accretion disk and the black hole. And that's what a quasar is. And the difference between a quasar and the blazar is only how we look at it. As you can see, a blazar is looking directly at us, while a quasar is looking the other way. And that's the only difference between the two of them. So what I started to do this summer first was to actually image the blazars as we expect. We're only going to see a point of light right there in the middle, and that's what it is. That's what I started doing. But then I moved on to my second project, which was viewing the Galactic Center. The Galactic Center has a lot of dust between us and what we can see. So we really can't see all the bright stuff that's behind the dust. But with radio imagery, we could kind of try and penetrate that so we could see what's going on. And why are we looking at the Galactic Center right now? Well, it's because right now there's an event going on that a giant gas cloud is actually going into a black hole. It's actually going to be torn apart by the black hole. Although, in actuality, it's not really happening right now. It happened already in the past. And here is a video simulation of what's going to happen. So as you can see, this color thing is actually the gas cloud, and this right here will be the black hole. This is only a simulation. And as you can see over time, it starts to speed up as it gets closer and closer into the black hole until it just kind of bursts all over the place. And this should help astronomers and stuff try and find more info, more insight onto how the mass reacts to as it gets closer to the black hole. So yes, there's the black holes. There's two types: those rotating, the non-rotating. And as I said before, it already happened in the past, 26,000 light years away. So it's not happening right now. Just to let you know. And the gas cloud is pretty long right now, 37 million miles. And that's what I'm observing. That's the data. So to process the data, I go through some computer program scripts, which I then go to image it each day for many months. And this is just the raw data. The raw data. It hasn't been filtered out or anything. These charts represent a phase over time. The phase is where the telescope array is looking at. And for each of these plots, say for this one right here, it'll be or 2 telescopes, and this one will be another 2 telescopes. So each 2 telescopes represents one baseline. And the farther away the baseline is, the more field of view, as I said before. So we could get all these baselines together and compile them all into one image. And this is the same thing, except for this one, it's still raw data. It's phase over the frequency. You really can't tell much by looking at this. You can't. So what I try to do, what we're trying to do this summer is go in through and filter out all kind of like the bad data, sort of, all the bad data from the antennas, and try and run some scripts that actually images the gas cloud going into the galactic center. And this is one of the first, this is at the highest frequencies we've done, which is almost 9 gigahertz. And as you can see, I'll play this sort of video. It only goes for from -15 to 15 arc minutes, which is half a degree of view. Although, as you can see here, some of the data is not that great sometimes. Might be some interference or something else is going on. Who knows? But we keep going. It's actually arranged by the frequency. As you can see, the frequency is going down. And as the frequency goes down, this object right here tends to get more brighter. The black hole is actually supposed to be at the 0, 0 mark at the center of this diagram. And to the right, the flux, this is the flux scale that we implement. So before I didn't start with the flux, but each has the same range. So all you're supposed to see is the center is kind of changing as the frequency goes down. And it's also, we did this for many months right now. It's still a work in progress. It's still a work in progress. And this is one of the first images I was doing, as the cell size and the image size was different. This is a smaller view. It's more zoomed in, actually. And the range, the scale, actually, is smaller as compared to this one. These two are the same images. So for the same day, although you can see the scale, we implemented the flux into this image when we ran the computer program to process this. Yes, so it's still a work. It's still a work in progress. You probably can't tell with this image, but it's a bit more square looking, and that gives us an idea that that's not really what's going on right now. So we filter out the bad data, and we get this more prettier picture on this. And with that same picture, what I'm doing right now is actually kind of slicing the pictures. I'm slicing the pictures into half-hour intervals, because for each night that the telescope observes the galactic center, it's about 2 or 3 hours. So this way, this picture is only for half an hour. And as you can probably tell, there's kind of like some blobs in here, which represents maybe some bad data. And that's also for another half hour. And if we combine these two images, we combine them, and that's for 1 hour. For the same day, but we combined the 2 previous images, these two, into that one. That's the 1 hour. And as you can see, it looks a little bit more cleaner, right? And if we combine these images, we could look and see for the whole 3 hours, and that looks a lot more cleaner. So even if we get something that looks kind of bad It might be just because we haven't exposed it as long for that certain day. So what we're trying to do now is to try and compile all the images into one image that we make it look nicer. So as to be, but we could also try to do for each day and each time interval to see what exactly is going on from time to time. And as I said before, it's still a work in progress. Our Galactic Center, that's supposed to be the representation of the gas cloud going into the black hole. It's pretty interesting, as you can see. As I keep saying, it's a work in progress. Hopefully this will give us more info as to how it behaves in a black hole. Like within the next year or so, we should start to see the gas cloud kind of bursting out. And for those of you that are really picky, it already happened 26,000 years ago. I got to catch up on that. Yes, so there's some of my references. And I want to thank SETI and Campare for giving me this opportunity to work over here. I want to thank my mentors, although some of them are not here. I want to thank all you guys for listening. It's been a wonderful summer. And I want to thank the black holes and the gas clouds for giving me something to look at. Thanks. Any questions?
Excellent. Do we have questions? Yeah.
So you've been taking images or making images that are plus or minus 10 arc seconds or 15 arc seconds?
It's 30 arc minutes, so it's half a degree.
Arc minutes, rather. I'm sorry. Do you have any calculations or any theories that tell you how close the gas is going to have to get to the black hole before it gets hot enough for you to see at microwave frequencies?
No, not yet, but I wish I had an answer for you. But that will be interesting to find out.
So is it just a theoretical prediction that in the next year the gas will start getting close enough to really burst, like in the simulation? Or do you have any evidence that that's starting to happen?
Well, there's been some work before, and it's been observed for over 10 years already. And you can probably see as a simulation, it gets faster and faster as it goes into the black hole. So any day now, pretty much.
That's pretty cool.
So our gas cloud is still small, right? It hasn't exploded yet. Mm-hmm. Do you know what the actual physical size of that cloud is? You know, like approximately how far across is it?
I looked up how long it was, and I looked 37 billion miles across.
Okay, 37 billion. So it's pretty small then. It's kind of like solar system size. That's
yes.
You know, I mean, that's something that you could measure in astronomical units, right? Mm-hmm. Okay. Because one thing you want to keep in mind when you're looking at time series data and looking for changes is that you're not going to see any meaningful changes that are small, that on a time scale shorter than the speed of light times the size of your object, right?
Right.
And so I don't know. You're looking at things over hours, and it's not clear to me whether we could even expect this gas cloud to change in hours. And there's a couple issues there, whether light can cross it that quickly, and then you have to worry about things like the speed of sound, like whether any signals within the cloud could change its structure. So I'm sort of wondering whether there's any advantage to looking at your data on just an hour by hour or day to day, or whether you just really want to stack it together so you get a better signal. What's the kind of right balance there?
We're still trying to find out what it is. Like, I could go down even farther from 30 minutes and go by seconds, actually.
Right, well, you wouldn't expect to see any meaningful changes in seconds. Yeah.
But what I'm trying to do now is actually compile the images into days. For the images that have all the same frequency, we'll have into one thing. So like sometimes for like a week, we have the same frequency, and then the next week we change the frequency a little bit lower, and that's how we keep going.
Okay.
Any other questions?
Yeah, so earlier in your presentation, you mentioned the non-rotating and the rotating black holes. Can you give us the difference between the two?
Just basically how they react. Like I forgot it was, the rotating one had a higher mass, so it probably could have a higher gravity. So that may or may not affect what we're looking at right now.
And is that related to how they formed?
Hmm?
Is that related to how the black holes formed?
In a way, yes.
Okay, let's thank our speaker. Good job. Okay, our next talk is by Deborah Hernandez, also from Cal Poly Pomona.
So hi, once again, I am Deborah Hernandez, and over this summer I was granted the opportunity to work with my mentor, Virginia Gulick, studying gullies on Mars, and more specifically, their fluvial geologic processes as evidence for liquid water on Mars. So just a little background, my data was gathered completely from the Mars Reconnaissance Orbiter. It was launched in 2005, and since its arrival, it has been gathering data since 2006. The instrument I specifically worked with was one of 6 on the Mars orbiter, and this was titled HiRISE, or the High Resolution Imaging Science Experiment. The operation center is at the University of Arizona. However, NASA, JPL, Ames, all managed to gather that information as well and do their own studies. And the orbiter actually orbits at around 250 kilometers above the Martian surface. So it becomes incredible when you look at the resolution as being 25 centimeters per pixel. It is unprecedented as far as our orbiters have gone, and they can resolve meter scale features. And this normally helps out just because it gives us vast detail as far as studying channels and valleys, volcanic landforms, and ancient lakes and oceans, to name a couple of the geologic formations. Here's a picture of the instrument itself, so it's pretty large. But one of the formations that is taken by those high-rise pictures are gullies. Gullies we normally see on Earth as seen by this picture from the New Zealand gully. Normally it's defined as a deep channel on a hillside, often cut by water erosion, and serves as drainage ways for the water to flow down along with the sediment transport of the sediment that is around that area. On Mars, however, there are several different types of gullies, and many have suggested that they may have been formed by different processes. And the gullies normally erode in bedrock and exhibit fluvial characteristics. Other examples of fluvial characteristics would be, again, if you look at Earth and their analogs as far as a stream bed. You can normally see that as a stream goes in a curving manner, kind of meandering back and forth, it normally tends to erode one side, where completely opposite on that same position in the river, you see a deposit of sediment as it cuts through the bank downstream. And we can also see longitudinal stream profiles, which when looking at concavities of these streams, we can see a distance. It basically graphs the distance versus the elevation of a stream. And so gullies normally form in the presence of deep slopes, such as valley walls, central peaks and pits, dune fields, and in my case, a crater wall. So the gullies are normally comprised of 3 different portions: the alcove, the channel, and the apron or the debris fan. Alcoves normally have a slope of about 20 to 25 degrees. Channels normally have a slope of about 10 degrees to 20 degrees, where the debris fan normally have slopes of less than 10 degrees. Gullies in general are more common on the southern hemisphere of the Martian planet. However, they do form in both the northern and southern hemisphere. So in these hemispheres, they are normally seen around the 30° to 50° in latitude. And we've also noticed that they are non-existent near the equator. And so the MOLA, or the Mars Orbital Laser Altimeter, have also studied that gullies occur at varying elevations between 500 meters to about 1,500 meters. And one of the most interesting things that we've managed to look at through these high-res images is that these gullies mostly, we normally see them on facing the poles. So that's a little snippet of characteristics in Martian gullies. So over the 10 weeks, my focus of study, I basically took longitudinal and cross gully profile studies. And these profiles were to help me calculate the volumes of the gullies through the apron, the channel, and see the deposition through the aprons from sediment movement. I also went ahead and looked at the profile concavities, or rather the curvature of erosion into the crater wall. And I also went ahead and looked at the sinuosities of these gullies, which was defined by Mangold as the ratio of channel length to the valley length. So it would normally be the ratio of, if you were to get your pencil and just put it through the middle of the stream and go ahead and curve out, go along the curves of the stream versus the actual length. So what helped me do this was looking through the high-res images and looking at two different models, such as the digital terrain model, the DTMs, as well as a digital elevation model, the DEMs, a little help with the anaglyphs, which was just a 3D representation of the Martian surface, as well as an imaging software program, ENVI and IDL. So basically, what did I do all day? Oh, actually, let me go back. Craters. The Corazal crater was my specific crater. We're actually looking at different craters. Another one was done by a previous intern who looked at Palliker crater. I personally looked at the Corazal crater. So this, you can kind of see it as a craterception. It's kind of a crater within a crater. So my crater was specifically located at 169.4 degrees longitude and a latitude of negative 38.7. I used the left observation as well as the right observation with a north azimuth of about 270 degrees, and my crater had a diameter of 8.33 kilometers. So the Corazal crater, here is an image of its location relative to the Martian surface. So here, this particular high-res image didn't take an image of the entire crater, but it did take enough of the crater for us to gather information from. And if you were to look, if I get this mouse going, we can see most of the gully craters. I'll go ahead and zoom in a second. We can see most of the gully craters are formed along the top part of this portion of the crater, whereas the bottom crater, virtually non-existent. And so, obviously, that's the area that I looked at. So these were the gullies that I looked at, and specifically went ahead and detailed their data. So there were obviously a lot more gullies. However, I chose the more defined gullies to run my experiments on. So basically going from A to L, and I didn't necessarily go in order, but it didn't really make much difference. Here's a little bit of a zoom up. So you do manage to see these highlighted ones are the gullies that I went ahead and took my data from. You do, however, see little underdeveloped gullies forming alongside as well. So normally what I would do, I would be given this picture. This picture is a digital elevation model of the surface of this crater. So visually, it's not the most pleasing to look at. You might first see it as just kind of a really blurred image of what could be a crater, when in fact it actually gives me a lot of information. So being as it's called a digital elevation model, it really does give me the elevation at these points. So I went ahead and did a center stream line going through the middle of the gully, and went ahead and did cross profiles all along that gully. And again, so you might be wondering, how was I able to figure out where these gullies were? That's where the high-res images come into play. These high-res images, although obviously a lot more visually stimulating, they don't give you that much information as far as elevation goes. If I were to go ahead and take a same profile on the ortho picture as well as a high-res picture, The high-res picture would go ahead and give me a graph plotting the transit length in meters versus its pixel shade. So again, not very informative. So this is an example of two profiles that I took, both on the high-res versus the ortho pictures. So the ones over on the left-hand side would be if I were to go ahead and make a profile on the high-res image. So again, the first one, very jagged. It looks like there's just, the pixels are everywhere. The bottom, you might think that, oh, you know, it's showing the same characteristics of a profile of what would be a normal stream, because you do get this stereotypical V shape. However, this part of the gully, and this transect in particular, was a more developed portion of the gully. So although it does create a V shape, it's because the pixels happen to be darker in that area. So as opposed to the images over on the right-hand side, where you see a more curved channel that was carved out by some sort of process. So this is what I would normally go off of in my data. And the results. So I went ahead and plotted a couple of parameters from these gullies, including their volumes, their concavity index, and according to their positions on the Corozal crater. So looking at the gully location, clockwise position in the Corozal crater from A to B, but with the other gullies in between, you see that there isn't much of a difference in slope, which proves to be fine for us because it serves as kind of a control, seeing as these gullies had an average slope of about 19 degrees with the minimal slope of 14 degrees and the maximum slope of 21 degrees. So again, there isn't much variety in slope, which we can then compare the differences in volume, eroded volume, and the concavity as well, which would be this next graph. So this next graph, although it seems a little random, I'm gonna have you guys do a mental note of this sort of trend that it has, a kind of sinusoidal wave of sorts. So this would be the gully location versus the volume that was essentially carved out of that gully. That same trend seems to follow with the gully location versus the stream concavity index. So that was a number derived from Shepard that basically took how concave the graph was as opposed to its highest elevation to its lowest elevation on the gully. Sinuosity, we also looked at the sinuosity of every single one of these gullies. These gullies had a sinuosity index number of averaging about 1.3, 1.3, with the lowest at about 1.9 and the highest at about 1.5, sorry. And this information, which is a little bit of extra information for us, and I compared it to Mangold's paper, where he had actually plotted out the sinuosity of different gullies around the planet itself. And my information falls right in between where he said that the sinuosity should be. So again, around 1.3, which would be depicted by this blue shade right here. The yellow shade would be about 1.1, and the orange would be less than that. So future work. We still have a lot of data gathering to do from my particular crater, such as drainage, the drainage area, the basin of sorts. We also need to finish analyzing the data because apparently, obviously, as you saw from those graphs, we saw that there is a definite relationship between the volume of erosion versus the stream concavity index. We also want to look at different craters, both southern hemisphere and northern hemisphere, and compare and contrast the difference in the crater data on Mars. And we also want to look at those values and compare them with terrestrial analogs, because again, if gullies on Earth are normally formed by water erosion, this could provide some insight as to what exactly is forming these gullies. So here are my references. I'm going to want to go ahead and acknowledge my mentor and another NASA intern, NASA employee, Sasha, for helping me doing my scripts. Dr. Phillips, Cal Poly, NASA, Campere, parents. But that, any questions?
Let me ask a first question. So is the region of gullies that you're studying, do you know how old those are? Like, are those actively forming, or is this like an older region where the gullies formed a long time ago and then aren't changing?
Well, the one that I was specifically given was, it is kind of like of interest to us because it's an RSL. So I guess they're trying to figure out what exactly is forming around. What I'm interested in looking at is looking at different flybys to see how active they are and how active the gullies are and whether or not they are forming in real time and how they basically change and develop over seasons or time or whatnot.
Right, because it seems like it'd be really cool to map out that, if you found a really young one and then you saw changes over time.
Yeah, because we can definitely tell, especially by geologic theories and whatnot, about looking at the different aprons. We can compare the gullies that are running alongside each other, that some aprons overlap the older gullies and their older aprons. So we can kind of look at relatively age them, I guess, in that sense.
That's cool. Other questions?
So why do you think all of the gullies form and kind of on one rim of the crater? And does this give us any clues as to, what causes them from happening?
Well, one of the theories that I kind of suggested, I haven't looked really further into it or read that many papers on it, but what I was kind of suggesting was kind of like how the bedrock, how the bedrock sits, basically, the angle of the bedrock. And so if the bedrock were to be sloped in a way that the water would go along that bedrock, it would be exposed. Whereas if you look towards the southern part of the crater, if that bedrock was still pointed north to south, there would still theoretically be some sort of liquid, but it wouldn't be exposed through the crater wall, but rather just through the crater subsurface, I suppose.
Do you think like the solar illumination matters at all? Well, it actually almost seems opposite from what I think. Like you think, the northern part of the crater is in shadow most of the time, right? Because in the southern hemisphere, and the southern part gets illuminated. So you can imagine if you needed something to melt water and free things up, but then you'd think, shouldn't it be on the southern side instead of the north? So it's kind of funny.
Yeah, and it's interesting because it does have those same characteristics on the northern part of the northern hemisphere as well. The gullies point towards the north. So.
Other questions?
Do you think the concavity and the sinuosity, the variations that you see in all your measurements, does that have something to do, like, why do you think they're there? Why do you think those differences are there?
The differences between what?
Say like the range in concavities that you measured, or the range in sinuosities. What causes that?
The range, I would assume just well, again, I don't think the slope has anything to do with it because we did manage to find out that there weren't varying changes in that, but probably just the amount of, I guess, liquid water theoretically that would be there. Maybe, I don't know. Yeah, I would just assume just the more water in that area, the more that it managed to take the sediment in that area.
So maybe it has something to do with their maturity, or like
exactly.
how long they've existed, that sort of thing.
Exactly. Yeah, and that's what I did notice because when looking at the different ages, or I guess how I did manage to see the different aprons overlapping, I took a look at the gullies that were essentially forming those aprons, and I did notice that the older gullies did have a higher concavity.
That could be interesting to look at. Awesome.
Yeah, so we still have a lot of data analysis to go through and go back and see if we can get any more data. So.
Other questions? Okay, let's thank our speaker. Nice job.
Thank you.
Okay, and our last talk this morning is by April Davis from MiraCosta College. Come on down.
Hi, my name is April Davis. My mentor is Janet Bishop, and I'm presenting on clay minerals at Mars Vallis using reflectance spectroscopy to refine the chemistry of Mars. The purpose of this presentation and of my research is to understand the history of water in Mars Vallis, to refine our knowledge of the chemistry of Mars Vallis, and look for biosignatures. I'll be giving you some background, procedures, and conclusions. So this is a picture of Bumpus Hell, where you can see the microorganisms chewed away at the clay and the ferric minerals to create ferrous minerals. And we do have something, okay, we do have ferrous minerals that we're trying to explain in Marth Vallis, but we're not looking at microorganisms. We're looking at formation in anoxic waters, leaching, and redox reactions as possible explanations. This is Marth Vallis. It's a Themis false color image. The blue is fine grained sediments. The red, yellow, and orange is larger rocks, gravel, so on. Oyama crater is about 100 kilometers wide, and Marth Vallis channel is about 15 kilometers wide. The regions in the red and white are where my CRISM data is somewhere in there. Those are really big areas. My CRISM data is not that big. Marth Vallis was formed during the Noachian period stratigraphy. That was about 4 billion years ago, and when scientists thought there might be abundant surface water on Mars. There's a minimal high temperature diagenesis, so there's not a lot of pressure and high temperatures changing the minerals in the area, and there's widespread phyllosilicates near the mouth and channel. So this is biotite and kaolinite. They're both phyllosilicates. Phylo is the Greek word for meaning leafy or segmented. Kaolinite you actually have to put under a microscope to see the plates. So what do I do all day? I make rainbows. Or at least that's what I thought when I first sat down at the computer and started working with this. And now when I look at them, I see so much more. I see uplift and erosion and compaction and something really beautiful, honestly. And at the 2.2 mark here, you can see, this is all visual hyperspectral near-infrared spectral data, by the way. At the 2.2, that should actually be aluminum silica. And you can see on the, let's make this, there we go. You can see that band there. And that's where the aluminum and silica is vibrating with the hydroxyl groups to make that. And it's really strong here at 2.29. So that's where most, that's where most of the minerals are in this. 2.23 is aluminum and iron. And you can see that in the pink and blue. These are all lab spectra data. It's from, each color is a different sample. So the red here, you can see it goes out a little, so it probably has a little more magnesium in it. Our areas of interest are 2.2 to 2.3 microns, and that's where the strongest bands usually are. 1.9, but, oh geez, no, 1.9, and that's water. 1.4, and you can see the same kind of interactions there, but it's a lot weaker. You can see here for the 907 how it has more aluminum and iron, and so that's where that 2.23 band comes from. And for 908, that isn't there, so you don't see that at all. These are my chemistry data plots, and this is just for the high iron ones that we were showing you. The pink ones are doublets, so you can see that the higher Fe in the sample, generally the higher it's going to be up here. You can see it better, so in other, you can see it better. I'm just going to stop using the mouse. You can see it better and if there's more on there. So here I am at the Rainbow Maker 5000. Usually graph making is really fun, but it's very involved and it's not terribly interesting, so I'm just going to leave it at this is where all the magic happens. This is my MRO CRISM data for 3BFB. It's a location, well, these tiny little arrows are pointing at pixels you can see off on the side, and those are where this data comes from. 119 and 174, the pink, geez, I'm just going to use, okay. 119 and 174 are the CRISM data, and that's for the relative IF is their y-axis, is a function of wavelength. And all the data at the bottom is lab sample data, and they use reflectance as a function of wavelength. So the 1.41 OH overtones, you can see they're not nearly as significant in the CRISM data as the 2.2. If you look at the green line, the 2.20, that correlates with the green spectra data, and that's the midpoint, and it shows us that allophane is probably where, is probably what that mineral is, or it has properties of allophane. and then the 2.21 for the purple, and it's also broader, showing what's potentially a acid leaching band at around 2.27, and that shows us that it's opal, or has properties of opal. There's also montmorillonite and bodolite, but in the same areas, but they're not on this graph. So here you can see we did in-column ratioing, and the bottom arrow is pointing to a really dark place. It's pretty boring. It's cap rock. It's dust. It's not very interesting. And so we use that to make spectral profile. We take that right there as the boring one, and we ratio it to other colors that we see. And these correlate to colors you'll see on the next slide. And when we're done, we have, you can see like a Fe2 slope here, like a iron 2 slope there, as compared to these. So here, so the orange ones were from like iron minerals, magnesium minerals. The blue are aluminum silicates. The green are ferrous clays. And the black is just dust and cap rock. Again, this is the 2.27 for the possible iron leaching here. And this is probably the closest one I came to finding anything on this. So it's really complicated making these slides, or making these graphs and determining what you're looking at. Everything's so close, and you can just look at, like this one's 2.32, and it's magnesium. And at first I thought, oh, these definitely have to have magnesium, but I was wrong. So I have a lot to do there. I'm going to go back and do that after I leave. I'm going to continue working on this and trying to compare them to different lab samples. I'm going to go collect some lab samples as well. These are the nontronites from the other slide, and you can see that oh, I should have brought notes up here. So you can see that, well, they're very close. They're very close to the saponites and the nontronites, but they're not exactly there, and I'll continue my research doing that. This image is, Alicia Knoll made this for me. She's a student of here working with Janice Bishop. It's a 2-time exaggeration, vertical exaggeration of CRISM on high-rise images. And I think it's really beautiful, and that's why I included it. But this area here is the area where we were looking at phyllosilicates. So you can see the blue better, and the ferrous clays, and the irons. So in conclusion, Marth Vallis is a good place to look for biosignatures because of the favorable environments and the lack of disruptive forces. And we can't really use CRISM data to search for organics because the 3.5 nanometer band is really noisy in that area, and that's where we would find them. Or life could be fossilized, and we wouldn't see them. And this is not fossilized life. This is from a meteorite in Mars that they thought was maybe life, and it wasn't. So where does that leave us? We really need something like the Mars Science Laboratory to find organics, but using reflectance spectroscopy gives us a pretty good idea of where we should land, or if explorers ever go to Mars, what they might see. And so these are my acknowledgments and references. I want to thank Dr. Janice Bishop for answering my thousands of questions, as well as my professor, Rika French, Alicia, and Chatal for all answering my questions, and the SETI Institute for giving me this opportunity. Any questions?
Very nice job. So, do we have any questions for April?
Yeah, so you mentioned that you obtained all of your data doing reflective spectroscopy. Can you go ahead and explain exactly what is reflective spectroscopy?
Yeah, so we're using the Mars Reconnaissance Orbiter CRISM, and the CRISM basically takes the sun reflected off of Mars, and that's how it sends us the data. And like the molecules, like the aluminum or the iron, they connect to the OH bands, and it causes them to vibrate and stretch and bend. So if there's more aluminum, then it's going to pull it closer to the 2.2 or 2.21. And if there's more iron, it's going to pull them closer to the 2.29 micron band.
Cool. Other questions?
You said that this was a good place to study because there weren't disruptive forces. What does that exactly mean?
So there's not a lot of high pressure and high energy happening there. So the biosignatures aren't being disrupted.
So there's like not as much like wind and
Well, there's not as much alteration of the minerals due to high pressure and high temperature.
So what could cause alteration of minerals? Like, are you talking about like volcanoes or lava flows or big craters? And what could alter them?
It's a pretty good question that I'm not sure that I know the answer to. So in this area, no, I just don't know. I'm sorry.
But it's just an area where they seem to be well preserved.
Yes.
In other words. Okay. Other questions? Okay, that's great. Let's thank April, and let's thank all our speakers for a really excellent set of talks this morning. So that'll conclude our presentations this morning. Thank you very much, and we appreciate your attention.